In the deepest places of our world's oceans, where sunlight has never touched, and where the weight of water above would crush any surface dweller in an instant, something extraordinary burns. Not the fierce, explosive fire we know from land, but something altogether more mysterious, something infinitely more peaceful. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you, make sure you're subscribed, because tomorrow I've saved something extraordinary for you. 2.5 miles beneath the surface of our seas, where pressure reaches 300 times what we experience at sea level, volcanic fire burns in absolute silence. Here, in perpetual darkness, lies Earth's most active volcanic region, a hidden empire of molten rock and gentle creation that has operated unseen for millions upon millions of years. Consider for a moment the scale of what lies beneath. While we marvel at the peaks of the Himalayas or the vastness of the Amazon, we remain largely oblivious to the volcanic mountain ranges that dwarf anything on our continents. The Mid-Atlantic Ridge alone, just one of these underwater giants, stretches 40,000 miles across the ocean floor. To put this in perspective, you could wrap this single volcanic ridge around Earth's equator 1.5 times and still have mountain left over. This is not mere geology. This is the breathing apparatus of a living planet. Every moment of every day, this hidden ridge system exhales molten rock at temperatures that would melt copper, creating new seafloor in a process so gentle that fish swim undisturbed mere meters above. The ocean's crushing weight, that same force that would instantly destroy any unprotected human, transforms what should be catastrophic explosions into something resembling an underwater ballet. Imagine witnessing this phenomenon firsthand. Picture yourself sealed within a steel sphere, descending through layers of blue that gradually fade to black. The pressure gauge climbs relentlessly, 10 atmospheres, 50, 100. Your submarine's titanium hull groans under forces that increase with every meter of descent. And then, in the eternal night of the deep ocean, you see it. A gentle glow emanates from cracks in the seafloor. Not the angry orange of surface lava, but something softer, more ethereal. Molten rock emerges like thick honey, flowing at the pace of a leisurely walk. As it meets the frigid seawater, it doesn't explode in violent fury as our surface experience might suggest. Instead, it crystallizes instantly into glass sculptures that catch and reflect your submarine's lights like underwater chandeliers. This is the ocean's pressure cooker effect in action. The immense weight of water above keeps explosive gases dissolved in the molten rock, like carbonation trapped in an unopened bottle. What would be devastating eruptions on land become Earth's most peaceful volcanic activity. The lava flows with the consistency of honey, cooling and hardening into formations that look more like art than destruction. But the true wonder of this hidden world extends far beyond the mere mechanics of underwater volcanism. These gentle eruptions are quite literally building our planet, creating new ocean floor at the steady rate of 2 centimeters per year. To human perception, this seems glacially slow. Yet over geological time, this patient process has constructed the very basins that hold our oceans. Every day today, as you listen to these words, underwater volcanoes add approximately 20 tons of new rock to our planet's surface. This fresh seafloor, born in the crushing depths, will eventually journey across ocean basins over millions of years before being recycled back into Earth's interior. It is a cycle so vast in scale and so gentle in execution that it operates completely beyond human awareness. Yet it is fundamental to the very existence of our blue planet. The pioneers who first glimpsed this hidden realm were among the bravest explorers in human history. In the 1960s, when we had barely begun to explore our own oceans, scientists descended into crushing depths aboard submarines that were marvels of engineering, steel spheres designed to resist pressures that would liquefy any conventional vessel. These early ocean explorers faced challenges that make space travel seem straightforward by comparison. While astronauts journey into the familiar vacuum of space, these underwater pioneers descended into an alien realm where pressure increases relentlessly, where communication with the surface becomes tenuous, and where a single structural failure would mean instant, catastrophic implosion. What they discovered revolutionized our understanding of our planet. The ocean floor was not the barren, lifeless desert that scientists had long assumed. Instead, they found a world of volcanic activity so extensive that it dwarfs all surface volcanism combined. 80% of all volcanic activity on Earth occurs beneath the waves, hidden from our view in the planet's deepest places. Consider what this means for our perspective on Earth's processes. While we focus on the relatively rare and spectacular eruptions that occur on land, Vesuvius, Krakatoa, Mount Street, Helens, the real volcanic action unfolds continuously in the deep ocean, as it has for billions of years. This underwater volcanism is not occasional or dramatic. It is constant, gentle, and absolutely essential to the functioning of our planet. The volcanic ridges beneath our oceans form a continuous mountain system that spans 65,000 kilometers longer than any mountain range on land. These underwater peaks rise 3 full kilometers from the ocean floor, yet their summits remain 1 to 3 kilometers below the surface. They are mountains that have never known sunlight, peaks that have never felt wind or rain, yet they are among the most geologically active places on our planet. The molten rock that emerges from these underwater volcanoes tells a story of deep time that stretches far beyond human comprehension. Each flow of lava carries with it a record of Earth's magnetic field at the moment of its creation. As the rock cools and solidifies, it locks in the orientation of our planet's magnetic field, like a geological compass frozen in time. Scientists have learned to read these underwater volcanic rocks like pages in a book, revealing the history of our planet's magnetic field over millions of years. They have discovered that Earth's magnetic poles have reversed many times throughout geological history, and these reversals are recorded with perfect fidelity in the volcanic rocks of the ocean floor. This hidden volcanic activity connects to systems far beyond the ocean depths. The heat released by underwater eruptions drives ocean currents that regulate our planet's climate. Warm water from volcanic regions travels thousands of miles, moderating temperatures at Earth's poles and making our planet more hospitable to life. The volcanic minerals released into seawater provide essential nutrients that support the base of marine food webs, making these underwater fires quite literally the foundation of ocean life. As we float here above this hidden volcanic empire, it becomes clear that our perspective on Earth's processes has been fundamentally limited by what we can see from the surface. The gentle, continuous volcanism of the deep ocean is not merely a geological curiosity, it is the primary mechanism by which our planet renews itself, creating new seafloor while recycling old materials in a cycle that has operated for billions of years. In the profound darkness of the deep ocean, where pressure would crush us instantly, and where temperatures fluctuate from near freezing to hundreds of degrees within mere meters, Earth's most essential processes unfold in perfect silence. Here, in places no human eye witnessed until just decades ago, our planet breathes through volcanic vents, creating and renewing the very foundations of our blue world. Tomorrow, we will explore what happens when this molten rock meets the abyss, a collision of fire and water that defies everything our surface experience suggests should happen. We will discover how the impossible becomes routine in the crushing depths, where the laws of physics create wonders that exist nowhere else in our solar system. The fire beneath the crushing deep burns eternal and peaceful, building tomorrow's world one gentle breath at a time. In the surface world, we know, when molten rock encounters water, the result is catastrophic. Steam explosions tear through the landscape. Volcanic ash clouds billow miles into the sky. The very air becomes unbreathable. This is the fury we associate with fire meeting water, a violent collision of opposing forces. But beneath the crushing weight of our deepest oceans, something altogether different unfolds, something that challenges everything we think we know about the fundamental nature of volcanic activity. At temperatures reaching 1,200 degrees Celsius, hot enough to melt copper coins or reduce aluminum to liquid, molten rock flows directly into seawater that hovers just above freezing. Logic suggests this should create the most violent explosions imaginable. Instead, it produces only the gentlest hissing sounds that travel for miles through the deep ocean, like whispered secrets. Consider what this means. The very laws of physics that govern explosive steam formation on our surface are transformed in the deep ocean into something entirely peaceful. The crushing pressure, that same force that would destroy any surface dweller, becomes Earth's great peacekeeper, preventing the violent steam explosions that would otherwise tear apart the seafloor. Picture this extraordinary scene unfolding in the eternal darkness of the abyss. Molten rock emerges from cracks in the Earth's crust at walking pace, glowing like liquid amber in the submarine lights. As it meets the frigid seawater, the intense pressure forces any steam to remain dissolved, like carbonation trapped in an unopened bottle. What should be explosive becomes meditative. The lava flows with the consistency of thick honey, advancing so slowly that deep-sea creatures can simply move aside and continue their daily routines. Fish swim casually around flows of rock hot enough to vaporize them instantly on the surface, protected by the very water that surrounds them. The ocean's crushing embrace transforms destruction into creation. As each flow of molten rock cools, it takes on shapes that seem almost deliberately artistic. The lava forms into pillow-shaped mounds, each one measuring 3 to 10 feet across, stacking upon one another like enormous stone cushions across the seafloor. These formations, appropriately called pillow lavas, create underwater landscapes that resemble nothing so much as giant mattresses where sea creatures make their homes. Imagine walking, if such a thing were possible, across these volcanic pillows. Each step would take you across rock that was once liquid fire, now cooled into sculptures more beautiful than anything human artists could design. The volcanic glass forms in seconds as the outer surface of each pillow cools instantly upon contact with seawater, trapping gas bubbles that create natural windows. Through these glass formations, bioluminescent fish swim like living stars, their light refracting through volcanic crystal into patterns of extraordinary beauty. The process creates structures of remarkable geometric precision. Each pillow forms as the lava's outer skin cools and hardens while the interior remains molten, continuing to flow and expand until it breaks through the cooled crust to form the next pillow. It is a process of birth and rebirth, each pillow giving rise to the next in an endless cycle of the creation. But the transformation extends far beyond the purely physical. The heat from these underwater eruptions creates phenomena that exist nowhere else on Earth. Warm water rises from the volcanic flows in invisible columns, like thermal elevators carrying nutrients and minerals upward through the ocean layers. These heat plumes can extend for hundreds of meters above the volcanic source, creating warm water highways that marine life follows like underwater migration routes. The volcanic heat creates temperature gradients so subtle and precise that they support entire ecosystems organized by thermal tolerance. Within mere inches, water temperature can vary from near boiling to near freezing, creating microenvironments that host different communities of organisms. It is as though the volcanic forces are painting with temperature, creating invisible landscapes that teem with life. The chemistry of these underwater encounters produces wonders that border on the magical. As seawater meets molten rock, minerals dissolve and recombine in ways that create entirely new compounds. The volcanic glass that forms contains trace elements from both the Earth's deep interior and the ocean's ancient waters, creating crystal structures that record the exact moment of their formation, like geological photographs. Some of these volcanic glasses contain perfectly preserved bubbles of gas from the Earth's interior ancient atmospheres trapped within crystal for millions of years. Scientists have learned to extract these primordial gases, discovering atmospheric compositions that existed when our planet was young, when the very air was different from what we breathe today. The sounds of these underwater volcanic encounters tell their own story. Unlike the explosive roars of surface volcanism, underwater eruptions produce a symphony of gentle sounds. The soft hissing of gas escape, the quiet crackling of cooling rock, the subtle pops of glass formation. These sounds travel vast distances through the ocean, creating acoustic signatures that marine life has learned to associate with the creation of new habitats. Whales and dolphins can hear underwater eruptions from hundreds of miles away, and some species appear to use these volcanic sounds for navigation. The acoustic signals from volcanic activity create a natural communication network that spans entire ocean basins, connecting distant volcanic sites in a web of geological sound. The volcanic flows themselves create underwater waterfalls as molten rock cascades down slopes and into deeper basins. But unlike surface waterfalls, these flows of cooling lava move in slow motion, taking hours or even days to complete their journey. Time itself seems different in the deep ocean, where geological processes that would be violent and brief on the surface become extended, meditative events. Each underwater eruption produces its own unique signature in the volcanic glass it creates. The cooling rate, the water temperature, the mineral content, all these factors combine to create crystal structures that are as individual as fingerprints. Scientists have learned to read these signatures like a language, deciphering the exact conditions present during each moment of volcanic creation. The beauty of these formations extends beyond the merely aesthetic. The pillow lavas create complex three-dimensional structures that provide countless hiding places and nursery areas for marine life. The spaces between pillows become underwater caves, where creatures shelter from currents and predators. The rough surfaces of volcanic glass provide attachment points for organisms that filter nutrients from the water. Over time, these volcanic formations become the foundation for entire reef systems. Corals and other sessile organisms colonize the volcanic surfaces, building upon the geological foundation to create biological structures of even greater complexity. The volcanic origin of these reefs provides the rhynovection, mineral-rich substrate that supports unusually diverse and abundant marine communities. The gentleness of underwater volcanic activity allows for a remarkable phenomenon: real-time observation of geological processes. Unlike surface eruptions, which are too dangerous and too violent for close study, underwater volcanic flows can be observed and filmed as they happen. Scientists in protective submersibles can watch new rock being born, witnessing geological processes that typically require millions of years to complete. This ability to observe underwater volcanism in action has revolutionized our understanding of how planets form and evolve. We can see, in real time, the processes that built our continents and ocean basins. We can watch mountains being born and new land being created. It is like having a window into the fundamental creative forces of our planet. The heat released by these gentle eruptions does more than warm the surrounding water. It drives ocean circulation patterns that affect global climate. The warm water created by underwater volcanic activity rises to the surface and travels across ocean basins, moderating temperatures and weather patterns thousands of miles away. The volcanic fires of the deep ocean help regulate the temperature of our entire planet. Tomorrow, we will explore how these individual volcanic events connect to form the most extensive mountain system on Earth. Underwater ridges that span continents and build new seafloor with the patience of geological time. We will discover how the gentlest volcanic forces on our planet are also the most powerful, shaping the very basins that hold our oceans. In the crushing depths where fire meets water, violence becomes peace, destruction becomes creation, and the impossible becomes the everyday reality of our living planet. Beneath every ocean on our planet lies a secret that would fundamentally change how we see our world, if only we could witness it with our own eyes. Hidden beneath miles of water, completely invisible from the surface, runs a continuous mountain system so vast it makes our terrestrial ranges seem like mere hills by comparison. The mid-ocean ridge system spans 65,000 kilometers across the floors of every ocean, longer than any mountain range on land, longer than the circumference of Earth itself. These are not occasional peaks scattered across the seafloor, but an interconnected network of volcanic mountains that forms the backbone of every ocean basin. Yet they remain almost entirely unexplored, their peaks hidden beneath 1 to 3 kilometers of crushing water. Imagine for a moment if we could drain the oceans and walk across this hidden landscape. We would find ourselves traversing mountains that rise 3 full kilometers from the surrounding seafloor peaks, taller than many of our most celebrated terrestrial summits. The mid-Atlantic ridge alone would reveal itself as a mountain range stretching from the Arctic Ocean to the Southern Ocean, a continuous spine running down the center of the Atlantic like a geological backbone. But these underwater mountains are fundamentally different from anything we know on land. They are not ancient, weathered peaks slowly eroding under wind and rain. They are young, active, continuously growing volcanic systems that add new rock to their structure every single day. They are, quite literally, the planet's construction sites, building new seafloor through volcanic processes so gentle they rarely disturb the marine life swimming overhead. Consider the extraordinary scale of this construction project. Every year, volcanic activity along these underwater ridges produces enough new seafloor to cover an area the size of Delaware. Over geological time, this patient process has built the very foundations of our ocean basins. The Atlantic Ocean itself exists because the mid-Atlantic ridge has been spreading its volcanic products outward for the past 200 million years, pushing apart the continents of Europe and Africa from North and South America. This is continental drift made visible, or rather, made comprehensible. The theory that our continents move across Earth's surface, once dismissed as impossible, finds its explanation in these underwater volcanic systems. The ridges continuously create new seafloor in their centers, while the older rocks spread outward, carrying the continents with them like passengers on an incredibly slow-moving conveyor belt. The volcanic process that drives this spreading operates with a precision that rivals any human engineering project. Molten rock rises from deep within the Earth, emerging through cracks that run precisely down the center of each ridge system. As the lava cools and solidifies, it creates new seafloor that immediately begins its journey away from the ridge, moving at the rate of 2 centimeters per year, about the speed at which your fingernails grow. To human perception, this seems impossibly slow. Yet over millions of years, this gentle but relentless process has carried rocks from the mid-Atlantic all the way to the coasts of Europe and America, rocks that formed at the ridge system beneath what is now the middle of the Atlantic Ocean, now support the beaches of Portugal and New Jersey, having traveled thousands of kilometers in their slow migration away from their volcanic birthplace. The underwater mountains themselves take on forms that exist nowhere else on Earth. Unlike terrestrial volcanoes, with their conical peaks and explosive craters, the underwater ridges create broad, rounded summits that stretch for hundreds of kilometers. Their slopes are gentle, carved by volcanic flows rather than explosive eruptions, creating underwater landscapes of surprising smoothness and beauty. These ridge systems are bisected by enormous valleys, rift valleys that run down their centers like geological highways. Some of these valleys are deeper than the Grand Canyon, cutting through the volcanic mountains to create dramatic underwater landscapes of cliffs, valleys, and plateaus. Within these rift valleys, the most active volcanic processes unfold, creating new rock in a continuous process that has operated for hundreds of millions of years. The volcanic rock that emerges from these underwater mountains tells the story of our planet's deep interior. Each flow carries minerals and gases from depths of hundreds of kilometers below the seafloor, providing scientists with samples of regions we could never otherwise explore. The chemical composition of mid-ocean ridge basalts reveals the nature of Earth's mantle, the vast layer of hot rock that lies between our planet's crust and its molten core. But perhaps most remarkably, this immense volcanic system operates with such gentleness that marine life not only survives, but thrives in its immediate vicinity. Fish swim undisturbed above active volcanic vents. Sea anemones attach themselves to fresh volcanic glass. Entire ecosystems flourish on the warm rocks of recently cooled lava flows. The ridges create underwater weather systems, with warm water rising from volcanic areas to create currents that flow across ocean basins. These thermally driven currents carry nutrients and oxygen to deep-sea environments, making the ridges not just geological features but biological lifelines that support marine ecosystems thousands of miles away from their volcanic sources. The magnetic properties of the volcanic rocks provide our most detailed record of Earth's magnetic field over geological time. As each flow of lava cools, it preserves the orientation of our planet's magnetic field at that moment, creating stripes of alternately magnetized rock that spread outward from the ridge like pages in an enormous book. Scientists have learned to read this magnetic history, discovering that Earth's magnetic poles have reversed many times throughout geological history. These magnetic reversals, recorded in volcanic rocks of the ocean floor, provided the key evidence that confirmed the theory of continental drift. The symmetrical pattern of magnetic stripes on either side of the ridge systems proved that new seafloor was being created at the ridges and spreading outward, carrying with it a perfect record of Earth's magnetic history. The construction process never stops. Even as you listen to these words, volcanic eruptions are occurring along underwater ridges around the world. New pillow lavas are forming, fresh volcanic glass is crystallizing, the ocean floor is growing, imperceptibly but relentlessly, adding to the foundation of our blue planet. The ridges also create underwater mountains that never quite reach the surface seamounts that rise from the ocean floor to within hundreds of meters of the surface waves. These underwater peaks, numbering in the tens of thousands worldwide, create isolated habitats where unique species evolve in splendid isolation. Many seamounts support endemic species found nowhere else on Earth, making them underwater islands of evolution. The volcanic heat from the ridges drives chemical processes that transform ordinary seawater into something far more complex. Minerals leach from the hot rocks into the surrounding water, creating chemically enriched environments that support forms of life unknown in other parts of the ocean. These mineral-rich waters become the foundation for food webs that exist independently of photosynthesis, deriving their energy directly from the geological processes of the Earth. The ridge systems also serve as natural laboratories for understanding how planets form and evolve. The volcanic processes we observe on underwater ridges today are similar to those that built the surfaces of other rocky planets in our solar system. By studying underwater volcanism, we gain insights into the geological history of Mars, Venus, and the countless rocky worlds that orbit other stars. Each ridge system has its own character, determined by the rate of spreading and the composition of the underlying mantle. The East Pacific Rise spreads rapidly, creating broad, low volcanic mountains. The Mid-Atlantic Ridge spreads more slowly, forming steeper, more dramatic underwater peaks. The differences reveal how variations in deep Earth processes create diversity in underwater volcanic landscapes. Tomorrow, we will explore one of the most revolutionary discoveries in the history of biology, the realization that these underwater volcanic systems support thriving ecosystems that challenge our most fundamental assumptions about the requirements for life. We will discover gardens of life that bloom in chemical soups heated by volcanic fire, where creatures grow to enormous sizes in the eternal darkness of the deep. The endless mountain builders work in silence and patience, constructing tomorrow's continents, one gentle volcanic breath at a time. hidden beneath the waves but fundamental to the very structure of our living planet. On February 15, 1977, 3 scientists aboard the research submarine Alvin descended into the crushing darkness of the Galapagos Rift, expecting to find the barren wasteland that scientists had long assumed characterized the deep ocean floor. What they discovered instead would revolutionize biology forever and challenge our most fundamental assumptions about the requirements for life itself. In the glow of their submarine's lights, they witnessed something that should have been impossible: a thriving ecosystem in the eternal darkness of the deep ocean, where temperatures fluctuated from near freezing to over 400 degrees Celsius within mere inches, and where life flourished without any connection to the sun's energy that powers virtually all surface ecosystems. Consider what this meant for our understanding of life itself. Since the earliest days of biology, we had assumed that photosynthesis, the process by which plants capture sunlight, formed the foundation of virtually every ecosystem on Earth. Yet here, in the deepest, darkest places of our planet, entire communities of organisms thrived in complete independence from the sun, deriving their energy directly from the geological processes of our volcanic planet. The volcanic vents, they discovered, act like underwater geysers, shooting superheated water rich in dissolved minerals 40 feet into the surrounding ocean. But unlike surface hot springs, these hydrothermal vents create environments of extraordinary chemical complexity. The water emerging from the volcanic depths contains hydrogen sulfide, methane, carbon dioxide, and dozens of other compounds that would be toxic to most surface life forms. Yet for the creatures that call these volcanic gardens home, these chemicals represent not poison, but abundance, the fundamental ingredients for biological processes that exist nowhere else on our planet. Bacteria that thrive in these chemical soups have evolved to derive energy from hydrogen, sulfide, and methane, forming the base of food webs that support creatures of remarkable size and diversity. Imagine witnessing these chemical gardens in their full glory. Giant tube worms, some reaching 8 feet in length, sway in the heated water like underwater palm trees. Their bodies, lacking any digestive system, host billions of bacteria that convert volcanic chemicals into nutrients. These worms have essentially become living chemical factories, their bodies serving as sophisticated vessels for the most ancient forms of life on Earth. Clams the size of dinner plates cluster around the volcanic vents, their shells gleaming white in the submarine lights. These bivalves, related to common shellfish but adapted to extreme conditions, filter the mineral-rich water through their gills, extracting both nutrients and the bacteria that serve as their primary food source. They grow to sizes impossible for their surface relatives, sustained by the abundance of chemical energy flowing from the volcanic sources. The bacterial communities themselves create underwater meadows of extraordinary beauty. Giant mats of bacteria spread across the volcanic rocks like colorful carpets, glowing with bioluminescence and creating living tapestries that shift and flow with the heated water currents. These bacterial meadows represent some of the most productive ecosystems on Earth, converting volcanic chemicals into biological energy with remarkable efficiency. The volcanic chemistry creates temperature gradients so precise that different species occupy zones separated by mere inches, like underwater neighborhoods organized by thermal tolerance. Near the hottest vents, only the most heat-tolerant bacteria can survive. A few inches away, where temperatures drop to merely warm, tube worms establish their territories. Further out, where volcanic heat mixes with the frigid deep ocean water, crabs and fish patrol the borders of these thermal oases. These temperature gradients create environments of extraordinary stability. Unlike surface ecosystems, which fluctuate with seasons and weather patterns, the volcanic gardens maintain consistent conditions year-round. The thermal energy flowing from deep within the Earth provides a reliable source of power that has operated continuously for millions of years, creating islands of biological stability in the variable deep ocean. The discovery of these ecosystems fundamentally changed our understanding of life's possibilities. If complex ecosystems could thrive around underwater volcanic vents, using chemical energy instead of sunlight, then similar communities might exist anywhere in the universe where geological processes create the right chemical conditions. The implications extend far beyond our own planet, suggesting that life might flourish around volcanic vents on the moons of Jupiter and Saturn, or in the subsurface oceans of distant worlds. The chemicals emerging from these volcanic sources tell the story of our planet's deep interior. The dissolved minerals carry signatures from hundreds of kilometers below the seafloor, providing scientists with samples of regions we could never otherwise explore. The sulfur compounds reveal the nature of deep Earth processes. The trace metals speak to the composition of our planet's mantle. Each volcanic vent serves as a natural well, bringing samples of the deep Earth to the surface where we can study them. But the volcanic gardens are more than just windows into Earth's interior. They are active participants in global ocean chemistry. The minerals released by hydrothermal vents circulate throughout the world's oceans, providing essential nutrients for marine life thousands of miles away from their volcanic sources. Iron from volcanic vents supports phytoplankton blooms in distant parts of the ocean. Sulfur compounds, released at volcanic sites, influence the global sulfur cycle. The life forms around these vents have evolved solutions to challenges that would be impossible to overcome on the surface. Some bacteria live at temperatures that would instantly kill any other known life form. Others thrive in water so acidic it would dissolve human tissue. Many organisms have developed symbiotic relationships so intimate that they cannot survive independently. Tube worms and their bacterial partners, for example, represent a single functional unit that combines animal and microbial capabilities. These symbiotic relationships reveal life's extraordinary capacity for innovation. The tube worms provide protection and concentrated chemicals for their bacterial partners, while the bacteria provide nutrients for the worms. This partnership allows both organisms to thrive in conditions that would be lethal to either species alone. It is cooperation at the most fundamental level, written into the very cells of the organisms involved. The volcanic gardens also serve as nurseries for deep-sea life. The warm water and abundant food sources create ideal conditions for the reproduction and development of many species. Young fish that will eventually migrate to other parts of the deep ocean often begin their lives in the chemical gardens around volcanic vents. The thermal oases provide protection from the harsh conditions of the broader deep ocean environment. Scientists have discovered that these ecosystems are remarkably diverse, with new species regularly found at each newly explored vent site. The isolation of individual vent systems, separated by hundreds or thousands of miles of cold, dark ocean, has led to the evolution of endemic species found nowhere else on Earth. Each volcanic garden is like a biological island, supporting its own unique community of organisms. The chemistry of these systems creates natural pharmaceutical laboratories. Many of the organisms that thrive in extreme volcanic conditions produce compounds that have potential medical applications. Heat-stable enzymes from volcanic vent bacteria are already used in biotechnology. Other compounds show promise as antibiotics or anti-cancer agents. The chemical gardens may hold keys to medical breakthroughs we have yet to imagine. The volcanic heat creates acoustic environments unlike anywhere else in the ocean. The superheated water creates distinctive sounds as it emerges from the vents, crackling, hissing, and bubbling that can be heard from great distances. Some marine animals appear to use these acoustic signatures for navigation, following the sounds of volcanic activity to locate the productive feeding areas around the vents. These sound signatures also allow scientists to locate new vent systems. Hydrophones, underwater microphones, can detect the acoustic signature of hydrothermal activity from hundreds of miles away, guiding research vessels to previously unknown volcanic gardens hidden in the deep ocean darkness. Tomorrow, we will follow the brave explorers who mapped these volcanic wonderlands for the first time, descending in submarines to Earth's most extreme environments and revealing a hidden world that has changed our understanding of life, chemistry, and the very nature of our planet. We will discover how each expedition into the volcanic depths revealed new surprises and expanded the boundaries of what we thought possible in the natural world. In the chemical gardens where volcanic fire feeds ocean life, the impossible becomes routine, and life reveals capabilities that stretch far beyond our surface-bound imagination. On January 23, 1960, Lieutenant Don Walsh of the United States Navy and Swiss oceanographer Jacques Picard descended deeper into our planet than any human beings had ever travelled. Sealed within the bathyscaphe, Trieste, a steel sphere suspended beneath a massive float tank, they plunged into the Mariana Trench to a depth of nearly 11 kilometres, where the pressure reached over 1,000 times that at sea level. Their destination was Challenger Deep, the deepest known point in our oceans, where they expected to find only lifeless sediment and crushing darkness. Instead, they glimpsed something that would forever change our understanding of life's possibilities, a flatfish swimming in water under pressure that should have made life impossible. This moment marked the beginning of humanity's systematic exploration of the deep ocean's volcanic regions, an ongoing adventure that continues to reveal wonders that challenge our most fundamental assumptions about our planet. Consider the extraordinary courage required for these early expeditions into the volcanic deep. While astronauts journey into the familiar vacuum of space, these underwater pioneers descended into realms where pressure increases relentlessly with every meter of depth, where a single structural failure would mean instant, catastrophic implosion, and where rescue would be impossible if anything went wrong. The submarines built for these expeditions represented marvels of human engineering. The Trieste's pressure sphere was forged from steel 5 inches thick, designed to resist forces that would crush any conventional vessel like an empty aluminum can. The walls had to be perfectly spherical. Any deviation from this ideal shape would create stress concentrations that could lead to catastrophic failure under the immense pressures of the deep ocean. Each expedition required submarines built like mobile fortresses, with titanium hulls and life support systems capable of sustaining human life for days in the most hostile environment on our planet. The crews faced challenges that make space exploration seem straightforward by comparison. In space, the pressure differential between inside and outside a spacecraft is just 1 atmosphere. In the deepest ocean trenches, that differential reaches over 1,000 atmospheres. Communication with the surface becomes increasingly tenuous as depth increases. Radio waves cannot penetrate seawater, forcing explorers to rely on acoustic signals that travel slowly through the water and can be distorted by thermal layers and underwater topography. The crews of deep-sea submersibles often work in isolation, as complete as that experienced by astronauts, but with the added psychological pressure of knowing that the ocean above them would crush their vessel instantly if the hull failed. The discovery of the East Pacific Rise volcanic system in the 1970s revealed underwater eruptions occurring in real time, providing scientists with their first opportunity to observe geological processes as they happened. Unlike surface volcanoes, which are too dangerous for close observation during active eruptions, underwater volcanic activity could be studied from protective submersibles, allowing researchers to witness the birth of new rock and the creation of new seafloor. These observations revolutionized geology. For the first time in human history, scientists could watch mountains being built, observe the formation of new ocean floor, and study volcanic processes that typically require millions of years to complete. The underwater volcanic systems revealed the mechanisms of continental drift in action, showing how new seafloor spreads away from volcanic ridges to push continents apart over geological time. Remote-operated vehicles equipped with sophisticated sensors began to map the volcanic landscape of the ocean floor in unprecedented detail. These robotic explorers, tethered to research ships by cables carrying power and communication signals, could venture into environments too dangerous for human crews. They recorded volcanic vents reaching temperatures of 407 degrees Celsius, while maintaining near-freezing water temperatures just meters away, creating the most extreme temperature gradients on Earth. The mapping of underwater volcanic chains revealed that 80% of all volcanic activity occurs beneath the oceans, making underwater volcanoes Earth's dominant volcanic process, despite being completely hidden from surface observation. This discovery fundamentally changed our perspective on our planet's geological activity. The spectacular eruptions that capture public attention on land represent only a tiny fraction of Earth's volcanic output. Each new expedition into the volcanic deep revealed surprises that exceeded the expectations of even the most imaginative scientists. The discovery of black smoke as hydrothermal vents that spew superheated, mineral-rich water into the deep ocean showed that the seafloor was not the geologically dead environment that scientists had long assumed. Instead, it was revealed as one of the most active and dynamic regions on our planet. The technology required for these explorations pushed the boundaries of human engineering. Cameras had to function under pressures that would crush conventional equipment. Lights had to operate in an environment where the pressure would compress any air-filled components to tiny fractions of their surface volume. Sample collection devices had to maintain their functionality while exposed to temperature extremes that would destroy most materials. The acoustic mapping of underwater volcanic systems revealed underwater mountains and valleys of breathtaking scale and beauty. Sonar systems that could penetrate the darkness of the deep ocean showed volcanic peaks rising several kilometers from the seafloor, underwater valleys deeper than the Grand Canyon, and volcanic plateaus extending for hundreds of kilometers across the ocean floor. These acoustic surveys also revealed the dynamic nature of underwater volcanic activity. Scientists discovered that some areas of the seafloor were spreading apart at rates they could measure from year to year. The volcanic ridges were not static features but active construction sites where new rock emerged continuously from the Earth's interior. The exploration of underwater volcanic regions required the development of new scientific instruments capable of operating in extreme conditions. Temperature sensors had to function accurately across temperature ranges that spanned hundreds of degrees. Chemical sensors had to analyze water compositions in real time while exposed to pressure that would affect the behavior of most chemical reactions. Water sampling from volcanic vents presented unique challenges. The superheated water had to be collected in special containers that could preserve its chemical composition during the long journey to the surface. Scientists developed sampling systems that could capture water at specific temperatures and pressures, maintaining the integrity of volcanic samples for laboratory analysis. The biological discoveries in volcanic regions required entirely new approaches to marine biology. Scientists had to develop techniques for studying organisms that lived in conditions lethal to most life forms. Specimens had to be collected and preserved under extreme pressure and temperature conditions. Many of the creatures discovered around volcanic vents could not survive the journey to the surface, requiring in situ observation and analysis. The exploration also revealed the global connectivity of underwater volcanic systems. Scientists discovered that some species found around volcanic vents had populations separated by thousands of miles of cold, dark ocean. This suggested that these organisms had methods of dispersal and colonization that allowed them to travel between distant volcanic oases, creating biological connections across entire ocean basins. The technological advances driven by underwater volcanic exploration have found applications far beyond marine science. Pressure-resistant materials developed for deep-sea submersibles have been adapted for use in other extreme environments. Sensors designed to function in hydrothermal vents have been modified for industrial applications. The remote-operated vehicles used to explore volcanic regions have inspired the development of robotic systems for space exploration. Each expedition into the volcanic deep expanded the boundaries of the known world. Scientists discovered that the ocean floor contained more active volcanoes than all the terrestrial volcanic systems combined. They found that underwater eruptions created new seafloor faster than it could be mapped. They realized that the deep ocean was not a stable, unchanging environment, but a dynamic realm where geological processes operated on timescales that humans could observe and study. The exploration of underwater volcanic regions continues today, with new technologies revealing previously unknown aspects of these systems. High-resolution mapping systems can now detect volcanic features as small as individual pillow lavas. Advanced chemical sensors can analyze the composition of volcanic gases in real time. Biological sampling systems can collect specimens while maintaining the extreme pressure and temperature conditions of their natural habitat. Tomorrow, we will explore one of the most remarkable discoveries of this ongoing exploration, the revelation that underwater volcanoes create perfect conditions for life to flourish in forms found nowhere else on Earth. We will discover how volcanic forces that seem destructive actually nurture and sustain biological communities of extraordinary diversity and abundance. The explorers of the volcanic deep continue to map Earth's final frontier, revealing a hidden world where fire and water create wonders that expand our understanding of what is possible on our remarkable planet. There is perhaps no more dramatic demonstration of our planet's creative power than the birth of a volcanic island. What begins as invisible fire burning on the deep ocean floor slowly builds upward through miles of crushing water, accumulating volcanic rock grain by grain, eruption by eruption, until it finally breaks the surface to create new land where none existed before. Hawaii represents the visible tip of this extraordinary process, a volcanic mountain that rises 9 full kilometers from its true base on the Pacific Ocean floor, making it taller than Mount Everest when measured from its actual foundation. Yet what we see above the waves represents only a small fraction of this massive geological structure. The bulk of Hawaii's volcanic foundation remains hidden beneath the ocean surface, a monument to millions of years of gentle underwater eruptions. Consider the patience required for such creation. The volcanic hotspot that built Hawaii has operated continuously for over 70 million years, creating a chain of underwater mountains that stretches 3,600 miles across the Pacific Ocean. Most of these volcanic peaks remain submerged as seamounts, rising thousands of meters from the ocean floor, but never quite reaching the surface. They form an underwater, the mountain range of extraordinary scale, invisible to surface observation but fundamental to the geography of the Pacific Basin. The process by which underwater volcanoes become islands reveals the remarkable persistence of geological forces. Each eruption adds only small amounts of new rock to the growing volcanic structure, but the accumulation over millions of years creates mountains of tremendous size. The volcanic hotspot beneath Hawaii produces approximately 10 cubic kilometers of new volcanic rock every 100,000 years, a rate that seems glacially slow by human standards, but represents enormous productivity by geological measures. As an underwater volcano approaches the surface, the nature of its eruptions begins to change. The crushing pressure that creates gentle pillow lava formations gradually decreases, allowing volcanic gases to expand and creating more vigorous eruptions. The transition from underwater to subaerial volcanism marks a critical threshold in the island-building process, where volcanic forces must overcome the cooling effect of seawater to build structures that can survive in the surface environment. The moment when a volcanic peak first breaks, the ocean surface represents one of the most dramatic events in geological history. Steam explosions mark the violent meeting of molten lava and surface seawater, creating spectacular displays that can be seen from great distances. But these initial explosive phases are typically brief, lasting only until the volcanic pile builds high enough above sea level to escape the direct influence of seawater. Iceland provides a unique window into this island-building process because it sits directly atop the mid-Atlantic ridge, where underwater volcanic activity occurs so close to the surface that the seafloor spreading process can be observed on land. The island represents a rare case where the underwater volcanic forces that normally operate in the deep ocean have built a structure large enough to emerge above sea level and continue growing in the surface environment. The volcanic processes that built Iceland continue today, with new eruptions adding fresh rock to the island's structure, while the underlying ridge system spreads the older rocks outward. This ongoing construction makes Iceland one of the few places on Earth where you can witness continental drift in action, as the island literally pulls apart along the line of the underwater ridge system. The unique position of Iceland allows scientists to study underwater volcanic processes without the need for deep-sea submersibles. The geysers, hot springs, and volcanic vents that dot the Icelandic landscape are surface expressions of the same forces that create hydrothermal systems on the deep ocean floor. The island serves as a natural laboratory for understanding how underwater volcanic systems operate and evolve. New volcanic islands continue forming today in locations where underwater volcanic activity has reached sufficient intensity to build structures approaching the ocean surface. Loihi Surmount, growing 900 meters below Hawaii's Big Island, adds new volcanic rock to its structure, with every eruption slowly building toward the moment when it will break the surface to become the next Hawaiian island. Current estimates suggest that Loihi will reach the surface in approximately 50,000 to 100,000 years, a brief moment in geological time, but an unimaginably long period by human standards. This ongoing island formation demonstrates that the volcanic processes that built our current island chains continue to operate, creating the foundations for tomorrow's terrestrial landscapes. The Galapagos Islands represent another remarkable example of underwater volcanism creating surface features. These islands emerged from underwater volcanic hotspots that created unique ecosystems both above and below sea level. The isolation of the Galapagos, separated from other land masses by hundreds of miles of deep ocean, allowed endemic species to evolve in complete isolation from continental influences. The underwater volcanic foundations of the Galapagos continue to influence the island's ecology today. Marine iguanas dive to graze on volcanic rock surfaces, feeding on algae that grow on the mineral-rich substrate. The volcanic chemistry of the surrounding waters creates nutrient-rich upwelling zones that support abundant marine life, making the Galapagos one of the most biodiverse marine environments in the world. The formation of volcanic islands creates opportunities for life to colonize previously empty ocean environments. The bare volcanic rock that first emerges from the sea provides a clean slate for biological colonization. Seeds arrive on ocean currents or carried by migrating birds. Marine organisms colonize the underwater slopes of the volcanic structure. Over time, these initial colonists evolve into unique island ecosystems found nowhere else on Earth. The volcanic nature of these islands continues to influence their ecology long after their initial formation. The mineral-rich volcanic soils support plant communities adapted to the unique chemical conditions. Volcanic heat creates microclimates that allow tropical species to survive at latitudes where they would normally be unable to establish populations. The ongoing volcanic activity creates new habitats while destroying others, maintaining a dynamic environment that drives evolutionary innovation. Some of the world's most remarkable endemic species have evolved on volcanic islands. The Galapagos tortoises, marine iguanas, and Darwin's finches all represent evolutionary responses to the unique conditions created by volcanic island environments. These species could not have evolved anywhere else, because the combination of isolation, unique habitats, and ongoing environmental change that characterizes volcanic islands exists nowhere else on Earth. The underwater, volcanic foundations of islands create unique marine environments as well. The steep slopes of volcanic islands extend deep into the surrounding ocean, creating underwater cliffs and valleys that support distinctive marine communities. Cold, nutrient-rich water rises along these underwater slopes, creating feeding areas for large marine animals including whales, dolphins, and seabirds. The volcanic processes that create islands also influence global ocean circulation patterns. The underwater topography created by volcanic seamounts and islands affects the movement of deep ocean currents, creating upwelling zones and mixing areas that influence climate patterns across entire ocean basins. The Hawaiian island chain, for example, creates a barrier that affects the flow of North Pacific deep water, influencing weather patterns across the Pacific region. The study of volcanic islands has revolutionized our understanding of how life colonizes new environments and adapts to extreme conditions. Island biogeography, the study of how species establish and evolve on islands, has become a fundamental discipline in evolutionary biology. The volcanic islands provide natural experiments in evolution, showing how life responds to isolation, environmental change, and unique geological conditions. The ongoing formation of volcanic islands demonstrates that our planet's surface continues to evolve and change. The volcanic forces that operate beneath the ocean surface are not merely maintaining existing features, but actively creating new land, new habitats, and new opportunities for life. The islands we see today represent only the most recent phase in a process that has been operating for billions of years and will continue for billions more. Tomorrow, we will explore how these individual volcanic events and island-building processes connect to form the grand cycles that regulate our planet's chemistry, climate, and the very conditions that make life possible. We will discover how underwater volcanic forces participate in global systems that maintain Earth's habitability across geological time. The islands born from the deep stand as monuments to the creative power of underwater fire, rising from hidden volcanic sources to become the foundations for some of Earth's most unique and precious ecosystems. Every morning as you wake to face another day, the hidden volcanic forces beneath our oceans have already been at work for hours, quietly creating approximately 20 tons of new seafloor rock while recycling older oceanic crust back into Earth's interior. This patient, continuous process has operated without interruption for billions of years, maintaining a perfect balance that regulates the chemistry of our oceans, the composition of our atmosphere, and the very conditions that allow life to flourish on our blue planet. This is the grand cycle that connects every underwater volcanic eruption to the maintenance of our planet's habitability. The gentle volcanic fires that burn in eternal silence beneath the waves are not isolated geological curiosities. They are essential components of Earth's life support systems, participating in global processes that make our world uniquely suited for life among all the planets we have discovered. Consider the remarkable precision of this volcanic recycling system. While underwater volcanoes create new seafloor at spreading centers along the mid-ocean ridges, older oceanic crust is simultaneously consumed at subduction zones, where one tectonic plate slides beneath another. The balance between creation and destruction is so finely tuned that the total area of ocean floor remains essentially constant over geological time, even as individual sections of seafloor complete journeys that span hundreds of millions of years. This recycling process transports more than just rock. Water, trapped within the mineral structure of oceanic crust, travels deep into Earth's interior at subduction zones, carrying with it dissolved chemicals from billions of years of ocean history. Some of this water returns to the surface through volcanic eruptions, bringing with it samples of the deep earth that provide our only direct knowledge of our planet's hidden interior. The carbon cycle depends fundamentally on underwater volcanic processes. Carbon dioxide, dissolved in seawater, reacts with volcanic rocks on the ocean floor, forming carbonate minerals that lock atmospheric carbon into solid form. When these carbonate-rich rocks are eventually subducted into Earth's interior, they carry their carbon cargo deep into the planet, removing carbon dioxide from the surface environment for millions of years. But the cycle does not end there. Deep within Earth's interior, the subducted carbonates eventually break down under extreme temperature and pressure, releasing their carbon back into the mantle. This carbon returns to the surface through volcanic eruptions, both underwater and on land, completing a cycle that regulates atmospheric carbon dioxide levels over geological timescales. This volcanic regulation of atmospheric chemistry has maintained Earth's climate within ranges suitable for life for billions of years. When atmospheric carbon dioxide levels rise, accelerated weathering of volcanic rocks removes excess carbon from the atmosphere. When carbon dioxide levels fall too low, volcanic emissions replenish the atmospheric supply. It is a natural thermostat, operated by underwater volcanic processes, that has prevented Earth from experiencing the extreme greenhouse effect that makes Venus uninhabitable, or the runaway freezing that has locked Mars in permanent winter. The heat released by underwater volcanic activity drives ocean circulation patterns that distribute warmth around our planet. Warm water from volcanic regions rises to the surface and travels thousands of miles before cooling and sinking back into the depths. This thermally driven circulation helps moderate global temperatures, carrying heat from equatorial regions toward the poles and preventing the extreme temperature differences that would otherwise make much of our planet uninhabitable. The mineral cycle operated by underwater volcanoes provides the chemical foundation for all ocean life. Every drop of seawater contains dissolved minerals that originated in volcanic rocks. Calcium for shells and skeletons, silicon for microscopic glass structures, iron for biological processes, sulfur for essential proteins. All these elements and dozens of others are supplied to the oceans through volcanic processes. The biological productivity of our oceans depends on the steady supply of nutrients released by underwater volcanic activity. Iron, from volcanic sources, supports phytoplankton blooms that form the base of marine food webs and produce much of the oxygen we breathe. Sulfur compounds from hydrothermal vents support unique ecosystems that demonstrate life's extraordinary adaptability. Trace elements released by volcanic processes enable biological functions that would be impossible without this geological input. The magnetic field that protects our planet from harmful solar radiation owes its existence partly to underwater volcanic processes. The movement of molten iron in Earth's core, which generates our magnetic field, is influenced by the thermal patterns established by volcanic activity. The heat released at mid-ocean ridges affects the circulation of material in the deep Earth, helping maintain the convection patterns that keep our magnetic field stable. The underwater volcanic system also serves as Earth's pressure relief valve, preventing the buildup of internal heat that could lead to catastrophic changes in our planet's surface. The continuous, gentle release of thermal energy through underwater volcanism maintains Earth's interior in a state of dynamic stability, allowing geological processes to operate smoothly over billions of years. The formation and the recycling of oceanic crust through underwater volcanic processes drives the movement of continents across Earth's surface. This continental drift has profound effects on global climate by changing the distribution of land and sea, altering ocean circulation patterns, and affecting the exchange of heat between different parts of our planet. The gentle volcanic processes of the deep ocean are the ultimate drivers of the largest scale changes in Earth's surface geography. The underwater volcanic system also influences the evolution of life itself. The movement of continents driven by seafloor spreading isolates populations of organisms, promoting the evolution of new species. The changing geography created by volcanic processes opens new ecological niches while closing others, driving the ongoing evolution of life on our planet. Climate regulation through underwater volcanic processes operates on timescales far longer than human civilization, but nevertheless affects the conditions we experience today. The current Ice Age cycle, which has characterized Earth's climate for the past few million years, is influenced by the arrangement of continents and ocean basins established by millions of years of underwater volcanic activity. The chemical composition of our atmosphere has been shaped by billions of years of interaction between volcanic processes and living organisms. The oxygen we breathe exists in our atmosphere partly because underwater volcanic processes have maintained ocean chemistry in ranges that allow oxygen-producing organisms to thrive. The balance of atmospheric gases that makes our planet habitable depends on the ongoing interaction between life and volcanic processes. The underwater volcanic system demonstrates the interconnectedness of all Earth systems. Geological processes influence biology, which in turn affects atmospheric chemistry, which influences climate, which affects geological processes. This interconnected web of relationships creates a planetary system that is remarkably stable and resilient, capable of maintaining conditions suitable for life even as individual components change and evolve. As we look toward the future, underwater volcanic processes will continue their patient work of maintaining our planet's habitability. New seafloor will form along mid-ocean ridges, carrying with it the chemical signatures of current ocean and atmospheric composition. Future geologists studying these rocks will be able to read the story of our current era, preserved in volcanic glass formed in the deep ocean. The timescales involved in underwater volcanic cycles extend far beyond human history and will continue long after our current civilizations have become geological history themselves. The volcanic forces that operate beneath our oceans connect us to the deep past of our planet and will continue shaping the environment for any future life forms that inherit our world. The eternal cycle continues as you listen to these words. Somewhere in the deep ocean, molten rock is emerging from Earth's interior to form new seafloor. Somewhere else, ancient oceanic crust is beginning its journey back into the planet's depths. The chemical elements that make up your body have participated in this cycle countless times, traveling from volcanic sources into the ocean, into living organisms, back into sediments, and eventually into new volcanic rocks. We are participants in the eternal cycle, temporary arrangements of elements that have been cycling through Earth's systems for billions of years and will continue cycling for billions more. The underwater volcanic forces that operate in crushing darkness and eternal silence are not separate from our daily lives. They are the foundation upon which all life depends, the patient geological processes that maintain our planet as a haven for life in the vast cosmic wilderness. The gentle fire beneath the waves burns eternal, renewing our planet one volcanic breath at a time, ensuring that Earth remains a blue oasis where life can flourish among the stars.